Thanks everyone for joining in here to this session, Better Plastic Part Design in SOLIDWORKS. My name is Ryan Navarro, and I'm a Senior Applications Engineer here with Hawkridge. And I'm joined on the line by Damon Tordini, who's our Product Manager for Plastic Simulation and Flow Simulation.
Thanks, Ryan. Good to be here.
Yeah, and so in this session, we're going to really be focusing on primarily the CAD side of things, basically tips for designing plastic injection molded parts specifically in SOLIDWORKS. So right at the end, we'll talk also about validation tools like plastic simulation that you can also use to validate and kind of rule out any molding issues or problems with plastic parts also. So some background on me. I've been with Hawkridge about 7 years now, and I teach a lot of our training courses and things online. And before Hawkridge, I did product design at a couple different companies, medical device company and also consumer products. So designed quite a number of injection molded parts and different types of plastic parts, roto-molded and things like that. And I've also learned a lot since then about modeling in SOLIDWORKS with Hawkridge. So I'm excited to present you these tips. And mostly we'll be focusing on a live example in SOLIDWORKS of building a plastic enclosure similar to this one here. So yeah, I did post at the top of the chat a design guide. It's really a zip file of a collection of publicly available design guides. I'll get into that in a second. But before we get into SOLIDWORKS, we'll discuss a couple different modeling approaches that you might use, because there's a whole lot of tools in SOLIDWORKS, and a lot of times it's kind of unclear which method, which road you should go down as you start out. And then again, we'll go into the live modeling example, which will be the bulk of the presentation, and then we'll circle back and talk about validating these things at the end. So if you've never had to design a plastic part before, I just want to, injection molded part specifically, a lot of these rules can apply to 3D printed parts too, but I'm sure a lot of you know, with 3D printing, you can do a lot crazier things also. So, but plastic injection molded parts, you hear these rules of thumb a lot of the times. Like we want to maintain a constant wall thickness, more or less. We want to have draft or like a taper essentially on all the vertical side walls and things so that it releases from the mold properly and we don't get any kind of scratching or cosmetic defects on the surfaces. You need to pay consideration to things like undercuts that we'll talk about more in a minute. And for cosmetic parts, or basically a lot of times it's any surface someone's going to touch, like soft touch surfaces that they're going to hold, or just cosmetic exterior faces of a product or something like that. If you're from the industrial design side, you'll probably care a lot more about the curvature and smoothness and all those parameters. And then on top of that, we need to make sure things are easy to assemble. So there's how it's going to be screwed together, glued together. Is there going to be snap fits and things? So there's a whole bunch of rules of thumb out there. And it just so happens that the companies that make the plastic, the polymer manufacturers, have kind of a vested interest in making sure that everyone kind of knows the rules to create parts. So in that zip file I attached, all those documents are basically publicly accessible. If you do just Google BASF Plastic Design Guide, you'll find one of those same PDFs. They're just kind of a collection. Actually, it's a few years old, that collection, so there may be newer ones now, but just a collection of a whole bunch of different resources. So for things like living hinges, snap fits, rib design, sizing ribs and things. So all these are rules of thumb. And again, they're in that PDF for your reference. But you may also sometimes run into situations where you're kind of in unknown territory and you can't rely on a rule of thumb. You can't have a wall thickness because of a constant wall thickness because of the way the part needs to be. And that's where things like the plastic simulation can really come in and help out. Let me know if anyone's having any audio issues or anything like that. Audio video issues as we work our way through. Just want to make sure that everything's coming across okay in the chat. And also feel free to send your questions into the Q&A. So if you have any questions, that's going to be the more efficient way to get them answered. So Other kind of considerations, I mentioned the fastening features. So when you look at a cross-section of some plastic parts, there may be ribs in there, there may be lips and grooves, what we call the different mating faces. Okay, cool. Sounds like the feedback is good in the chat there. And there's a whole lot more you can do. I'd say a common industry design trend, probably more so in like the past 20 years now, has been to integrate as much as you can into those molded parts. So integrated wire management clips for electronic. A lot of our customers deal with electronics, so integrated standoffs for things. So just reducing the part count that you might need in these plastic parts. And then it's always worth, even if you're on the part design side strictly, it's always worth considering what the mold is going to look like. So these are actually some screenshots from our mold tooling class. So if I click ahead here, I just wanted to highlight these red components. The red components here are what we'd call like side actions or slides, and they're actually necessitated for these little tiny parts that you see here. They're necessitated by these little tiny features, like this little tiny side cut on this, what it would probably be like a fastening clip or something like that, is what's actually necessitating these giant red side actions in the mold. So undercuts is what I mentioned earlier. Anywhere you have an undercut, potentially will drastically increase the complexity of the mold. And so that means it's going to take longer to make, it's going to be more expensive, and it may also limit the number of cavities that you can fit in the mold or number of parts that can be molded at a single time. So that's a big consideration to bear in mind before you even get into SOLIDWORKS is, okay, are we, how many undercuts do we want to have? How many cavities does the mold need to be? And basically it's a lot of info to process, but coordinating with your mold vendor, being in close contact with them if you're outsourcing the molding, or if it's in-house, even talking to them and gaining an understanding of what they're comfortable with, what they can and can't do, is really useful. And another just random tip, it can even be useful to just visualize it by creating a quick negative in SOLIDWORKS, like a Boolean subtract, to see what the mold tool steel is going to look like from your part design. And one of the nice things to think about also with that is if you have any tight fitting parts that need to be sized really tightly against each other, think about what's going to be material safe for the mold. So meaning if you think you're going to need to tune fitment a little bit of parts, like say it was that big hole, the circular hole in this thing, you might want to actually, you want to start off in what's called material safe for the mold. So wherever they're going to need to, remove material from the mold, that's good, because it's not possible really to put material back in, right? You end up in a very expensive situation if the change is not material safe and you're asking for material to get added back onto the mold somehow. A lot of times that might mean just having to have a whole new insert machined for the mold. So try to picture that negative state of the mold also. Okay, so that's just all background aside, and I think those PDFs will be helpful for that. The next thing is how we're getting into SOLIDWORKS. How do we start modeling these things? So there's some simple geometries that you can accomplish with just solid modeling features, like electrical connectors is a good example. Our extrude feature has draft built into it, and there's a lot of other features have draft built into them, so you can just build with solid modeling features if you want to. I'd say probably the majority of models fall into what we call this hybrid modeling category, where you use a mixture. You can use some solid features to represent maybe the bulk of a shape, and then we also might use some surface modeling features that we'll talk about. And then there's some models that just don't have a flat face on them anywhere that might require pretty much entirely surface modeling to build. So you can think of it kind of as a spectrum between how prismatic or blocky the parts are to how much they're just one continuously curved surface in terms of the modeling approach you're going to need to use. So with surface modeling, if you do decide to go that way, you have to do, or it's definitely recommended to do a lot more planning up front. So That would be things like creating some nice detailed sketches of what the model is going to look like, and then potentially even planning out kind of the surface structure that you'd be using to build the model, because we'll be building it like one face at a time with this workflow. And then that's just what it is constructing a whole bunch of reference surfaces, and whether they're sweeps or lofts or boundaries, and stitching together the model one surface at a time until you end up with an end result that is actually a solid in the end. So this gives you a huge amount of control, but it's also it's a steeper learning curve. And there's a lot of situations where you can actually get away with starting off with solid features and then just mix in the additional detail. So we do have a class just on surface modeling if you're interested in that we'll talk about. But for this demonstration, I was going to focus mostly on that middle of the road approach, which I think is probably what most of our customers should be using when it comes to creating moderate complexity plastic parts. So we'll be focusing on this for a live example. And the design inspiration here was basically just I Google searched plastic enclosure and took some of the first hits that came up for images and thought, okay, that looks like something we could probably make in 30 minutes. So that's what we're going to be doing here. All right, so I'm going to get into SOLIDWORKS, and I'm going to shut off my webcam just so I'm not hopefully covering up any part of the interface. And all I have here as a starting point is some initial sketches. So you'll see I have a top sketch that's created with some lines and arcs, and then I have also some different profiles for the sides. So I really want to show how if you use this hybrid approach of mixing the solid features in, how quick this process can go. So I am going to start off with an extrude, but before I even do that, one of the things you might want to do, and I don't always do this, but you might want to use global variables or equations. So under the Tools pull-down menu in SOLIDWORKS, you can go to Equations right here. And then there's a section called Global Variables. And this is useful for parameters that you basically want to reuse in your design. So we mentioned we're going to want to have draft. So if I put in a variable here called draft and hit Tab, I can set this to my draft angle. So I'm going to make that 3 degrees for this model. And it's important to put the units on here. We'll talk about that in a minute. Also, the wall thickness, that's another parameter that I'm going to be reusing frequently. So I'm going to call this just wall, tab, and then this is going to be taboo for some people, but I always, just from my experience, because the vendors I worked with are overseas, I always think of the wall thickness in millimeters, even though I'm modeling in inches. So sorry, but I'm going to type in here 1.6 millimeters and hit tab, so that gets converted to the appropriate inch value there. If you don't type in the units in an equation, then SOLIDWORKS assumes that it's just the units that are set in your document. So it would think actually that that's 1.6 inches. So I'm going to click OK and accept that. So those are just variables that live up top here that can re-reference in this equations folder. So now I'm going to model half the part. So I have kind of half the shape I want here to start with, and then we'll mirror it later on. I'm going to just do an extrude feature, and that shape is just made up of a couple arcs. And I'm going to build the top and bottom all at once, and then we'll split them up. So I'm going to extrude it blind up 1 inch and then blind down, let's just say 4 inches there. And this little button allows me to turn on draft. So I'll turn on draft in each direction. And instead of typing in a draft angle, I'll hit equals, which lets me reference those variables and set it to those variables I set. So this means if later on the molder says, hey, actually we need 4 degrees of draft, I'll have one spot, I'll be able to change it across the whole project essentially. So I'll click OK to create that, and then I can hide that sketch. So it's just a real crude drafted shape right now. And one of the problems with this method is it drafts all the faces. When you use that draft button in the extrude, it drafts all the faces. So we also drafted these faces right here. And I'm gonna eventually want to mirror across that right plane. So that creates a problem for me. So this is where I'm actually going to use my first, what we call hybrid modeling feature, which is I'm going to create a sketch on the front plane and just sketch a line that's sufficiently long that it covers the entire shape of the part. And then I'm going to go to my surfaces toolbar. So if you don't have this toolbar in SOLIDWORKS, you just right click one of your command manager tabs and you go on down to tabs and you can turn on surfaces. And I know we'll be going through this quick, but as a reminder, you'll have access to the recording of this session too, to review it if you want to. So with the surfaces tab active, I'm going to do an extruded surface, and I'll do this one. I like to use these right click menus. So I'll do this one mid plane and just make it, again, sufficiently long that it covers the entire part. We have a surface there that represents the faces I want, and we can use a command called replace face. So replace face is under my surfacing toolbar, and it expects me to choose the faces I want to replace. So I'll right click and select other to be able to choose the two faces through to the solid body there. And then I choose the replacement target, which is going to be this face. And then if I just right click, it'll do that. So it actually pulled those faces flush to the right plane, essentially. And now I can go and hide that surface. I don't need it anymore. Okay, so to start making this look a little bit more like the enclosure, we have this other sketch here that I created. It's just, again, a whole bunch of lines and arcs. You could use splines if you wanted to be a little more stylized. But with this here, I will do a extruded cut. Let's see, extruded cut. And that's just going to be a through all. So again, we're just using solids and the traditional cut features that we're used to. So now we're starting to get kind of the rough profile that we might want for this. So the fillets are what's going to make it look a lot more pleasing. Normally, I would say apply your fillets closer to the end of the modeling tree, but in this case, these are going to be really big fillets I'll be using, and I want them on sooner. So I'll go into my fillet shortcut and start clicking these edges. So one of the benefits of modeling the top and bottom at the same time is I can apply the fillets to both of them. I can do operations to both halves. Again, we're eventually going to split these halves apart. I can apply operations to both halves at once. So that's a 3/4 inch fillet. And if we use regular circular fillets, they're not quite as cosmetically pleasing as some of our other options. So I'm going to set this to curvature continuous, which is one of the options in SOLIDWORKS. That just means as these other faces are curved, it's going to kind of blend smoothly in and out of those curves. And the end result there is that when we switch off, if we switch off the shaded with edges display, you shouldn't be able to see kind of the sharp line that you would get there with a regular old circular fillet. It should blend a little more smoothly across that shape. So actually, a lot of times I may switch off shaded with edges and just look at the shaded display if you're working on something where the aesthetics are really important. Okay, so a couple more fillets to go. I don't want to bore you with these, so I'm just going to kind of speed through them. But the order of your fillets is quite important. So I'm rounding over that sharp edge. So I have one continuous set of edges that runs all the way around for my next fillet. And for this next one, I'm going to use not an edge fillet, which is the default, but a face fillet. So this third option, it's a little more work to set up. You have to select a pair of faces. And we'll lower it down to a smaller size, like 1/4 inch. And this is right now set curvature continuous, but you'll see that it tapers down. So when you set the size for a fillet normally, it doesn't really look at the width of it's a radius. So if the angle of the faces changes, the size, the apparent size when someone looks at it is also going to change. there's an option in here called chord width. It's only available when you're using a face fillet. And that actually maintains the chord, or the kind of edge-to-edge measurement of the fillet. So you can see the difference there between the symmetric, which gets really big in some spots and tiny in others, and the chord width, which maintains a really consistent, smooth appearance the whole way across. So that's what I'm going to use there. And there's a lot of places where a chord width fillet will look quite nice on your model. Okay, so the top is actually a little bit overbuilt right now. I didn't want it to be that that tall, and I did that on purpose because I don't want that to be flat. If you talk to a lot of industrial designers, they really don't want anything flat on the model. So I'm going to take care of that by creating a sketch on the front plane here. We'll do another kind of hybrid modeling operation. So I'll create a sketch on the front plane, and I'll go normal to that plane. And the first thing I'm going to do is just create a center line. So create a center line off to the right, and I'll dimension that to be the distance that I want my surface to actually start from. So that's going to be 3/4 of an inch up. And then it's just going to be another arc. I tried to keep this intentionally simple, so just a shallow arc. And the key to getting this to mirror across correctly is going to be to make that tangent to that horizontal center line. So because the arc is tangent now, it's always going to end there. The other thing I could have done is set wherever the center point of that arc is, I could have set that vertical to the origin if I wanted to. Should be equivalent. So I'm going to give that a radius, and we'll make that really shallow, like 80 inches. The larger the radius, the more shallow it's going to appear to be. And if I just cut that across an extruded cut or something, it would be still flat in one direction. So I'm going to do a revolve. So I'm going to zoom out quite a bit, and I'm going to sketch a revolve axis. So it could be a swept surface would be another way to do it if you wanted to go even more detailed. But revolves are a really nice, simple way to produce these shapes. So I'm going to make that 40 inches down. So you can see the revolve axis will be quite a ways down. And we could do this as a solid revolve cut by all means, but since we're talking about hybrid modeling, I'll show here how I could revolve surface, and just choose that for my axis. So you see there what it wants to do. And then I don't really need this to be blind. I could set it to be mid-plane and just kind of sufficiently long that it intersects that body there. And then I could use replace face again, but here I'll just use cut with surface. So cut with surface, and all you need to do is choose the surface and then make sure that that arrow is pointing the way you want. So you throw away the correct chunk of material. And then one of the nice things I think about this is also you can, if you want to make adjustments to it, if you're tweaking it as you go, if you turn on the instant 3D in SOLIDWORKS, then if I access that revolve surface, then anything I want to adjust, I can basically click and drag and see kind of the dynamic adjustment of it. It's not too apparent on this one, but it's a nice way to make those little tiny tweaks that you need to do to the model, rather than coming all the way back and editing the sketch and then bouncing back out again. So let me now hide that surface. And by the way, we're building kind of a collection of surfaces that I'm not going to need eventually. So we have in the feature tree a solid body, and then we also have these surface bodies. I'd highly recommend getting rid of these surface bodies eventually, which we will do. Otherwise, someone else that comes in might get confused by them. They can cause problems in other add-ins for SOLIDWORKS like simulation or CAM. So we'll get rid of those eventually. Okay, so if we look at some of our standard views, you'll see that now it's curved in kind of every direction. And those other enclosures had some big heavy chamfers around them. So that's going to be one of my last details here, chamfer. And I'll just right click, select tangency around this set of edges, and set a chamfer here. And I'll set this to be pretty shallow, kind kind of emulate that appearance that I want. So let's look at it without the edges on, and seems like it's starting to be where I want it to be. When you're working on half the model, you can't really get a perfect sense of what the whole thing is going to look like. So if you're not sure about the shape, then I would definitely mirror it and take a look at it. So I'll select my right plane and mirror, and then choose bodies to mirror here. Bodies to mirror the entire thing. So I'll select the shape there and click the check mark. And now we've got the whole shape mirrored over. And I can start to get a sense for what it might look like in terms of the proportions and everything, if I need to make a change anywhere. It's kind of basic on the bottom. We could do more on the sides and things to make it look better, but we're getting there. So then if I want to go back and make changes, though, I'll roll back above that mirror feature, because probably the changes I want to make, I don't want to have to do them across the whole model. So this is kind of a nice way to just quickly see the whole thing and then continue working. So we have one unused sketch here, which was a kind of partial cutout I wanted to do. So I'll go and do that now. And I'll do an extruded cut with this. It's not going to be all the way through, though. It's just going to be 1.5 inches. And we need draft on that vertical face on the left side. But if I try to turn on draft from this direction, cutting from this direction doesn't do what I want. It would draft the top face, but not the right side. So I'll have to add the draft separately. So if I click the check mark, right now that face is vertical, but I can add draft to this face using the draft feature. So I'll just come up to my command manager, regular features, and draft, and do a regular neutral plane draft here. So we choose the plane that represents the pull direction, which is my top plane. Make sure that arrow is pointing down. Select that face, and then I'll just do my equals again. Equals draft, 3 degrees. So we put that draft on. You definitely want to draft before you add any fillets or anything. And then, as you can expect, we'll be doing the second round of fillets here. So just give me a moment to get through that. Pretty much, there shouldn't be a whole lot of, on a product like this at least, I wouldn't expect there to be hardly any sharp corners. So again, starting with the biggest fillets first, usually. And then just kind of being intelligent about the way I apply the sequential fillets, so I end up with one nice loop at the end. So this last selection is going to go all the way around. And then again, just kind of gut check the model here. We can roll down past the mirror and see what it's looking like. You may even want to turn on perspective or something to get a better sense for what the model might look like. Okay, I think I'm almost done with the core things here. One of the last things I want to do is put an indent on the top, or what you might call like an inset face, because there may be an LCD screen or something that's going to get mounted in here. So that I could do before or after the mirror. I think here I'll actually do it after the mirror. So I'll create a sketch on my top plane. I'm just going to click on that face and offset entities, and choose the distance in that I want to offset, and reverse it so it's pointing in. So that's going to be my shape for my inset face. Now, if I rotate, you'll see that I'm not really in the correct plane to be cutting. So I could have created another plane. If I go to extruded cut, it's going to want to start from there. But I find a lot of people forget you have these different options here for where you want to cut from. And if I have a reference, like a nice reference, like my other revolve here, I can show that sketch that I used for that. And then I could use something like a vertex for reference. And I could just pick that point right there so that the cut will start from that vertex. So the depth I'm setting is starting from that point, and I'll set the depth I want down 2 inches. I do want to produce a flat surface underneath. So it'll be 2 inches, and I'll turn on the draft again, equals draft. And the number of places the draft angle creeps in gets bigger and bigger as you work on these things. So I do like that global variable approach. And I'll just hide the sketch when I'm done with it. Okay, so I'm getting there. So let me save this. I haven't even saved my work. I'm sure all of you know not to do as I'm doing here. And right now, this is all one solid body. So you might be wondering, well, this needs to be upper and lower half. How are we going to get to that state? So I'll pick on that top plane, and I'll do an insert, features, split. So split actually splits bodies up into multiple chunks. And this is part of what we call master modeling in SOLIDWORKS. You can create the one kind of cohesive shape you want, and then split it, cut, and we'll basically cut this, click these little scissors, allows us to cut it into two different bodies. Eventually we can save them out as two different files. But for right now, I'm just trying to cut them into two different bodies. So I'll click the check mark to accept that. And now we should see if I try to hide one of these, I can actually hide or show one half or the other. So I have this big whole solid chunk here. We're going to end up shelling this out to the desired wall thickness pretty soon. I also still have those surface bodies. So there's a nice shortcut. If you hit Tab on the keyboard, it will hide whatever body you're over. And if you hit Shift Tab, it will bring that back. So it's kind of visual wherever you have the mouse cursor. Shift Tab should bring them back, but then with things like the surfaces there, it gets confused and brings back the surfaces sometimes. So I think it's as good a time of any to clean up those surface bodies that I was using. And the way I'll do that is with the delete keep body command. So I'm actually going to select the two bodies I want to keep, right click, and choose this delete keep bodies here. And then I'll set it to keep. So basically, if I had a dozen reference surfaces, it would delete all those, and it's just going to always keep these two bodies. The reason I like using keep rather than deleting the reference surfaces is as long as this delete keep bodies at the end of the tree, it's going to get rid of whatever reference surfaces there were. So you'll see if I roll back above that, it has the two surface bodies there. And then when I roll back down, they're gone. So that's what I'd recommend using towards the end of your tree to get rid of those references so they don't confuse someone else. So now we've got our two separate halves, and I can easily hide and show them using that Tab and Shift Tab. So let's try shelling them out. And I will click on the shell feature. And basically you want to click the face you want to remove. So that's the face of the top plane there. And then here I'll do the equals, and I'll go into access that wall thickness variable that I created. And shelling is where you're liable to run into problems. So if you had fillets and really just dirty geometry that wasn't as clean as it could be, then you might not be able to shell correctly. But in my case, that one worked fine. Let's try our luck on the other side. I could have shelled first, but the reason I'm doing these two separate is they may not always want to be the same wall thickness. You might decide later on, maybe the upper piece can be thinner wall thickness than the other one. So that's why I'm doing two separate shell features. The little bit of time that you save by shelling them together, I don't think is worth it compared to the fact that you might want to vary their wall thickness later. Okay, so we've got them shelled out. So if we look at a cross section or anything like that, it's completely hollow right now. Just got the wall thickness that we specified. So this is kind of where the actual fun begins, where we can start adding in ribs, adding in fastening features, and things like that. Probably one of the main things we want to do while we have this in what's called the master model, while we have it in one part file, is we want to establish all the mating surfaces. So any interactions that are going to be shared between the lower and upper part, we want to define. So things like the lip and groove that will go around the edge to join them. If there were going to be screw bosses and things that join them together, we'd want to set up all those on the combined model here before we end up saving out the top and bottom as separate files. But just to show some of what we can do, I'm going to start off. I'm going to try to add some ribs to this lower file. So housing, we have a rib command we can use. And I don't want them to start all the way from this top plane. So this is a case where I will create a reference plane and offset it down to kind of whatever distance I want these ribs to start from. So I'll sink that down into the part quite a bit and then create a sketch on there for ribs. So the ribs are used to stiffen up any housing or anything. And one of the weird things about the rib command, different from a lot of other areas of SOLIDWORKS, is it doesn't have to go like coincident to the ends of the model. So I can just draw a line that's not touching anything essentially, and I can draw some other little lines here, and it's basically going to extend those until they intersect the other faces of the model, more or less. So I'm just drawing these kind of little line segments, and you would want to dimension them in practice, but I just want to cover more features here in the time we have. So when I click the rib feature with this sketch selected, you can see it wants to point down. It wants to apply a wall thickness here. Typically, the ribs don't want to be the full wall thickness that you have. They want to be some proportion of that to avoid sink marks. So I can still reference the wall thickness variable though, and then I can type in like times the little asterisk times like 0.6, which is one of those rules of thumb you might find in those design guides. I'm going to do 60% of the wall thickness. So it's still associative there. And then we want to use draft, but we don't want to do the full 3 degrees. I'll show you what that would do. It would get really, really thick near the base. So if I select the body there and click the check mark, you'll see it extended all those ribs. But when we look at it from the top, you can see how very extremely thick they're getting, because we're only enforcing the wall thickness at the top of them. So, and in fact, this may not be a great rib layout, but the amount of draft you might use on a rib might be more like a 1/2 degree or 1 degree. So I'm going to do a 1/2 degree there, and see that should not be nearly as drastic. And then you could tune these up. You could cut them back a little bit if they want to be closer to the surface. So there's other things we could do to improve the rib design. But I'm going to basically want these on both sides. So instead of trying to mirror the rib feature, I'm going to do it all in one rib command here. So I'm going to sketch a little center line and then use mirror sketch entities and copy over the rib to the other side. And then that will allow me to also put in some here if I wanted to have like a little one in the back and some little vertical ribs, just to kind of show how much you can load into just the rib command. It's pretty powerful. There are fallbacks for it. If it doesn't work for what you wanted, then you could always do like a thin extrude and do some more manual manipulation, but you can create some pretty complex rib patterns. They don't have to be 90 degrees to each other like this either. They can be circular arcs and all kinds of funky patterns that you want to be using. So then in terms of fastening features and things like that, let me bring back that upper half for a second with the Shift tab to show that body. If we go to Insert pull-down menu once again, we have a tab for fastening features, and we have things like snap hook. We have things like snap hook groove. Oh yeah, we had a question comes in. It sounds like on can the bottom of the rib be a percentage of the wall? Yes, there is an option here. So with the thickness, you can define the thickness at the sketch plane or at the wall interface. So if you do it at the wall interface, it'll go from bottom up, and the problem is it might not generate if it turns to like a sharp corner or something like that. But yeah, that is a great question. You can use at wall interface, and it'll try to keep the nominal wall at the interface where it touches the wall. Okay, I was just talking about fastening features. So these are like pre-built, kind of like macros almost for building different feature types. If you want a mounting boss and snap hook, I don't have a ton of time to go over all of these, so I wanted to focus on lip and groove, which I think is one of the cool ones. And lip and groove is specifically for situations like this where you have two parts that need to fit on each other. Industrial designers would call it a reveal. that you can produce there. So this part is a flat parting line, so you could just use like a cut on one side and extrude on the other. But when you have a non-planar parting line, this lip groove feature is very handy. So insert fastening feature lip groove, and it basically wants me to choose the upper part as a body and then the lower part as a body, and then a reference for the parting line. So I'll choose that top plane here. And then it basically hides one half of the screen. So I choose the what's going to be the groove face. They're calling the groove is going to be this little face here, and then I choose an edge that will belong to the groove. So I'll choose that interior edge, and you'll kind of see there it wants to put a groove cut in to this body. So then when I click into the other field, lip selection, it hides that body and shows me the other one. And I basically do the same thing on this side. I choose the mating face, what I want to be the mating face, and then I choose its own edge. And admittedly, these can be tricky to set up, these fastening features, because they've got a whole lot of numbers here. So thickness, desired gap, a desired draft angle, all these things. But if you do take the time to tune them in, then you can save them as favorites. So that's actually what I did. I have a load of favorite here. So I have a little favorite that's saved out pre-configured. So that just pulls in, make sure I have all the right parameters I wanted to be using loaded in here. So you'll see this favorite or styles option in a lot of different places in SOLIDWORKS. You can save your presets of values that you might reuse from file to file, and load them in as kind of on demand as needed. So we'll see if I got my selections right here. If I click the check mark, this is a very common error message to get, unable to maintain draft essentially. So if I click OK, it's not the end of the world. You can see it put in a lip and a groove feature. And if I were to look at a cross section, you can see what it did there. It notched one and added the other one. And we can also kind of see that this lip that it added is not drafted. So we can take care of that manually. Maybe I need to shrink one side too. It's not a very even split there, but okay, let's add the draft in. And how can we tell if we have draft? Well, under the Evaluate tab, there's a bunch of different options. There's draft analysis. There's also an undercut analysis that'll visualize undercuts for you. Wall thickness analysis you can do. So draft analysis, I can choose a reference like the top plane. And if it's set to 3 degrees, then I should expect everything to be green except for the ribs. And if I set down to the 0.5 that the ribs were at, then everything should be green looking from this direction. But we can see that little yellow sliver face of the undrafted part of the lip. So if I click the check mark, it'll actually leave this draft analysis up on the screen. And I can go to features and draft here. And this time I'll use a kind of a more complex mode of the draft command called parting line, which is useful. Again, this is a planar parting line, but if it jogged up and down, if you have something curved edge that you need to draft, use this parting line mode, because this lets you choose the top plane as my draft reference. And then I'll basically right click and select tangency to select the edges that I want to draft along. And you can see those little arrows pointing up. So even if those edges were jogging up and down, it would be able to draft them, or try to at least. And again, draft angle here, I'll match the existing sidewalls. So that's the draft global variable. Click the check mark and we can see that now all those turned green. It may produce some kind of patchwork faces there, so that's something to be aware of. But when we go to shaded with edges, or shaded with no edges rather, it's looking pretty good. So this would probably be a good spot to split them up. I would probably add screw bosses or something, but say I want to get these as 2 separate files now. There's a bunch of different workflows for doing that, but the easiest, simplest one to show, right-click on the solid bodies folder and save bodies. And then it'll prompt you so you can save these parts. And it wants to save them. I could have named the bodies better, but here it looks like having trouble even telling which ones which. So let's X out and let's rename these. I'll rename the body top and the other one bottom. And then we'll do the save bodies command. Okay, and then when I click the little save icon, it'll save these with their file names. And we can even create an assembly. I can create a assembly right here too, all within this thing. So when I click the check mark, it's going to create new SOLIDWORKS part files that inherit those bodies. So it's a type of external reference. And this is, again, part of what we call the master modeling workflow. So it's still showing me my part here, but when I scroll down to the bottom of the tree, you can see there was a save bodies command there. So this is now what I'd call the master model. And then if I minimize this, there's actually other stuff here. So I have actually, this is an assembly. If you look, this is an assembly, and it's got two different parts in it now. And if I were to open one of these parts, it's just got one, this part has just one feature that says stock. So it imported the stock from the master model. So now we have kind of like a spider web of references, but this actually means that now you could have two different designers, one person working on the top and one person working on the bottom. So if they need to add more detail and things into this, you can do that. So things that are not shared between both halves, like if I need to add the cutout for the screen that's going to fit into here, and those type of details, those are things I could do in this state where it's not necessary to have both the top and bottom there to be able to just, for instance, like put in a cutout for the screen. So I could add those type of features right here. Inside this stock model, build up additional features on top of this, and then I can end up having an assembly where we have those advanced features. We can insert in the electronics and the other things we need into here. But when we ultimately come back to the original model, master model that started with, we don't see any of those additional details, right? So from the when you're in one of these models where it's inheriting the stock, you have the option to right-click on it and edit it in context if you ever want to kind of jump back to the full master model. It'll bounce you back there. So that whole process we do cover in our surface modeling class, if you're interested. Kind of last thing I just wanted to show, and this is just very brief, is I wanted to give a shout out to some of the advanced pattern types that we have available. So things like curve-driven patterns, sketch-driven patterns can really make quick work of repetitive features. So this is just a slightly more detailed version of that upper housing. I have a rib, a little rib that's acting. In this case, it's using the option to go normal to the sketch there. And then instead of creating a whole bunch of ribs this time, I'm using a curve-driven pattern. I have a little sketch that goes all the curve essentially that goes all the way around. And I can have a curve-driven pattern, allows me to easily vary number of instances. So I can do 6 instances of ribs there and just have that instantly update. So even though it's a pretty complex geometry, SOLIDWORKS has all kinds of advanced pattern types that you can use to vary things like this. So explore the different pattern types that are in here: curve-driven, sketch-driven, fill pattern, variable pattern. Will really save you a lot of repetitive monotony as you're working on these types of files. Okay, so that was our demonstration. We talked a little bit about validation. All I had time to really show was the draft analysis, but realized there is an undercut analysis in there too that will highlight for you undercut areas, and wall thickness analysis that'll color code areas you have thick regions of wall thickness. And then we also have additional tools you can add on to SOLIDWORKS. So all the tools we showed were in SOLIDWORKS standard so far, but there's a SOLIDWORKS plastic simulation that you can add on that allows actually validating the plastic parts here. So let me bring myself back here and take a quick look at that. So SOLIDWORKS Plastics Simulation is an additional product that can be purchased, comes in a few different levels, and that's a mold filling simulation. So it actually allows you to predict things like ease of fill of a part, how much injection pressure would it require. But more notably for part designers, it allows you to predict defects. It allows you to predict things like sink mark locations and weld lines, and testing out different possible injection locations for the part, testing out different materials and seeing how it fills. And then also from the basic version of SOLIDWORKS Plastics has expansion opportunities for more advanced capabilities. So besides the things like sink mark prediction, it allows you to get into like cooling optimization, cycle time optimization, predicting the thermal behavior of a part. If you're working with fiber-filled, glass reinforced or carbon fiber reinforced materials, looking at how those materials will be distributed in the mold. And then even on the high level, things like warpage predictions and residual stress prediction in a plastic part. So very powerful simulation tool that you can take a look at if you're interested in it. And then I know we're at our time, so I just wanted to quickly cover some of the learning resources you have available. There's tutorials built into SOLIDWORKS for actually a lot of the topics that I went over. If you look at your SOLIDWORKS tutorials, there's multi-body parts. There's this one, Molded Product Design Advanced, that goes over a basic master model workflow. There's the Hawkridge Systems YouTube channel, which we fill with as many resources as we can for modeling and simulation. There's also happens to be for plastic parts specifically, some great third-party resources I can point out. So there's two product development companies putting out great YouTube tutorials using SOLIDWORKS, the DeMonte Group and Spanner Product Development. So if you search DeMonte Group YouTube, SOLIDWORKS, or something like that, you'll find their videos also. Definitely worth checking out. And then the paid options. So we offer training courses, live instructor-led training courses for these subjects. And the two notable ones, depending on where you're at, if you've gone through the basics of SOLIDWORKS and things, SOLIDWORKS Advanced Part Modeling and SOLIDWORKS Surface Modeling are two awesome courses if you're doing anything related to plastic part design. Advanced Part Modeling goes over a lot of the splitting and combine and subtract and splines and those types of solid modeling features. And then surface modeling starts off with kind of that hybrid modeling approach that I showed you, and then escalates through building a full dedicated surface model. Also, just as a shout out, in the near future, we're hoping to have a more advanced surfacing class also available. So if you took surface modeling already and you're looking for more, we'll be going through a really full-on detailed surface model with curvature continuity the whole way across it to come in a future course offering. But again, I just want to thank everyone for attending. Hopefully you got a lot out of this. Don't forget to download the zip file with all the PDFs in it. And I'll take this remaining time for Q&A. I'll come back to some of these questions that we had. Oh yeah, what did we choose on the cover to create the curve for the ribs? That's a great question, and I should have shown it earlier. Basically, I created a plane. Here, and then I just did like a convert entities from one of those fillet lines. And then what I did is I did a fit spline on top of it, if I remember correctly. So let's actually see the procedure I used. Actually, it was a 3D sketch. So I did a 3D sketch. I must have right-clicked. Let's see, let's go back in time. I want to make sure I get exactly what I did. Yeah, I did a 3D sketch before the fillets were there. So I took kind of that virtual sharp, and then I converted that edge. Select tangency, convert entities to get all that info right there. And then the thing is, curve-driven patterns, for something like this, it just works better if it's in a 2D sketch. So that's why I created a separate plane. And then I kind of reconverted entities into a 2D sketch from that 3D sketch. But the key thing, I think the key trick was scrolling back above before I had put these fillets on. So I didn't mention that either, but a lot of small little fillets that you might add, like these tiny little fillets that I added on top, I actually tend to add those after the shell operation, even though it's more of a pain because you have to end up adding them to both sides, the inside and the outside, and also kind of predicting what radius it needs to be correct on each side. But tiny little fillets like that tend to be what will break your shell feature. So, these are fillets that I would add very late towards the very end, because I just don't want perfectly sharp corners there. But I would actually consider adding those after the shell to both sides of the geometry. Let's see what else we got. Yep, and I think we did answer that question. If you go back and modify the master model, these other parts, as long as they have this reference, this is an external reference indicator. So you can see actually that's pointing to the other part file. So they will get updated when that other file updates.